Good morning, gentlemen, and welcome back. Today is April the 20th, Monday, and we are going to continue today with our discussion of Chapter 14, oscillations. But specifically today, we're going to talk about the idea of pendulum motion. Now, we've covered a lot of this already in previous sections, and so this shouldn't be too much new material, but we're going to apply it in slightly different ways. So, what is pendulum motion? All right. Well, first, when a pendulum is swinging back and forth, when it reaches its apex, or any time that it's not at the equilibrium point, there is a restoring force located here that's pulling the pendulum back toward the equilibrium point. Now, if you were to measure the angle theta between the string or whatever it is holding the bob at the end here of mass m, then there is an arc, and there's an arc length here which we call s. Then we can talk about the tangential restoring force for a pendulum of length L as F net equals the inverse of mg, or weight, divided by that length times the arc length S. So this is exactly the same formula that we saw as the linear restoring force as with a spring, but the constant is weight over length, the ratio of weight over length, instead of the spring constant. Now, the oscillation of a pendulum is, of course, simple harmonic motion. And so we can use the equations of motion written in terms of the arc length or the angle. And so the displacement, or S, the arc length, is going to be the amplitude times the cosine of the quantity 2 pi frequency times time. Or the angle theta can be given as the at a given time can be given as theta max times the cosine of 2 pi times the frequency times the time. Now, it turns out that a short pendulum is going to swing with a higher frequency than a long pendulum. All right, the longer a pendulum is, the slower it will swing. The longer its period, and the shorter its frequency. And so, if you have stronger gravity, all right, that will increase the restoring force. But gravity, generally speaking, for most pendula, is a constant, and that will increase the frequency. But increasing the length of the pendulum decreases the frequency, and therefore makes the period longer. The frequency can be obtained from the equation for frequency on a mass on a spring by substituting the quantity m times gravity divided by L for the value of k. And so frequency is given as 1 over 2 pi times the square root of the quantity g over L. And the period can be given as the inverse of that, or 2 pi times the square root of L over g. So the frequency and the period of a pendulum of length L with the free fall acceleration g, or 9.8 meters per second squared. As for a mass on the spring, the frequency does not depend on the amplitude, right? Remember, yesterday's, or actually the last lesson that we did, we noted that the amplitude of the pendulum doesn't affect the frequency. And so the frequency, and therefore the period, is also independent of mass. So it doesn't matter how heavy the bob is on the end of the pendulum. The only thing that influences the frequency is the length of the pendulum. Okay, and again, if you look at this equation that you see over here on the right, notice that mass is not part of the equation. So let's try an example. Example 14.10, designing a pendulum for a clock. A grandfather clock is designed so that one swing of the pendulum in either direction takes 1 second. Okay, so 1 second, 1 second. All right. Um, what is the length of the pendulum? All right. Well, one period of the pendulum is 2 swings. Okay, so there and back again. So the period is going to be 2 seconds. Now, the period, again, is independent of mass, all right? So it doesn't matter how heavy the bob is, and it depends only on the length. And we know that the period is equal to 1 over the frequency, um, which is equal to 2 pi times the square root of the length divided by the acceleration of gravity. If we rearrange this equation for L, we find that L is going to equal the acceleration of gravity times the quantity period over 2 pi squared. So plug and chug here, and we end up with the length of the pendulum to be 0.993 meters. And so there's your grandfather clock. If any of you have a grandfather clock in your house, you know that if it runs fast or it runs slow, you can move the bob up or down on the pendulum itself, and that will actually change the rate at which it tells time. So if the clock is running fast, you want to um, uh, bring the bob down a little further. If the clock is running slowly, you got to bring the bob up a little bit. Okay, so there we go. Now, a physical pendulum is very similar to that kind of pendulum, but this time the mass is distributed over the entire length of the pendulum itself. And so now, because the mass is not concentrated on the end like it is here, it's going to be concentrated at the center of gravity, which is located here. And so the position of the center of gravity of the object is at a distance d from the pivot point, which is located here. And so now, instead of the length of the pendulum becoming important, it's going to be the distance between the pivot and the center of gravity. So the relationships mathematically are all still the same. The only difference here is that now we're measuring the length or the distance between the pivot and the center of gravity, as opposed to the entire length of the pendulum. Now, let's see. So the moment of inertia, I, is a measure of an object's resistance to rotation. Increasing the moment of inertia while keeping the other variables equal should cause the frequency to decrease. In an expression for the frequency of the physical pendulum, we would expect moment of inertia to appear in the denominator. So when the pendulum is pushed to the side, a gravitational torque pulls it back, right? The restoring force pulls it back. The greater the distance d of the center of gravity from the pivot point, the greater that torque will be. Increasing this distance while keeping the other variables constant should cause the frequency to increase. In an expression for the frequency of the physical pendulum, we would expect distance to appear in the numerator. Okay, so what happens here is that we essentially have derived this equation from the information that we just read. So frequency here of a physical pendulum is going to equal 1 over 2 pi times the square root of m times g, but instead of all being over L, it's going to be distance divided by the moment of inertia. And so the term is the square root of mg times d over I. So let's look at another example here. All right, a student in a biomechanics lab measures the length of his leg from hip to heel, because your leg is essentially a pendulum. And so he finds that length to be 0.90 meters. What is the frequency of the pendulum motion of the student's leg? And what is the period? So we can model a human leg reasonably well as a rod of uniform cross section. All right, that's not completely true, but it's close enough for government work. It's going to be pivoted at the hip, and the moment of inertia for a rod pivoted about its end is equal to 1/3 ml squared. All right, so the length is still playing a role here. The center of gravity of a uniform leg is at the midpoint, and so distance is equal to L over 2. So how do we calculate this? Well, the frequency of the physical pendulum is given by the equation that we derived earlier. All right, that's shown here, 1 over 2 pi times the square root of mg d over I. And so now we plug and chug here, or actually just kind of replace. We've got the mass times gravity times the quantity of distance is replaced with L over 2, and the quantity for I is replaced with 1/3 ml squared. Doing a quick bit of canceling out, notice the masses go away, the length in the numerator disappears, and the square disappears here. And then if I forget what they call this in math, flip and do something else, but 1/2 over 1/3 is 3 over 2. And so the final formula for this particular case is going to be 1 over 2 pi times the square root of the quantity 3/2 times g over L. Now we just plug and chug. The expression for the frequency is similar to that of a simple pendulum, but with the additional numerical factor of 3/2 inside the square root. And therefore, the numerical value of the frequency turns out to be 0.64 hertz. Okay. Now, if the frequency is 0.64, we take the inverse of that and find a period of 1.6 seconds. Notice that we didn't need to know the mass of the leg in order to find the period. The period of the physical pendulum does not depend on the mass, just as it doesn't for the simple pendulum. The period depends only on the distribution of the mass. So when you walk, swinging your free leg forward to take another stride corresponds to half of the period of this pendulum motion. For a period of 1.6 seconds, this is 0.80 seconds. And so for a normal walking pace, one stride in just under 1 second it sounds about reasonable. Okay, my friends, your homework for tonight is to do the problems 25 to 34 odd numbers only in section 14.5 at the end of chapter 14. Thank you and happy Monday.